Okay. Right, let me see if I can get my presentation up and running. Get to the first slide here. First slide, yeah. I'm gonna see if I can get that to point to the correct page. Tell me if you can see the correct first page. Hans, can you see my presentation?
I can see it, but you must go to presentation mode.
Oh, you're seeing a different screen then. Okay. Why is this happening? I think it happened.
It always happens when you load up. You must go to presentation mode.
Can I go again? Start from first slide, but now I have to go back here and select a different screen. I think it's this one. Tell me if you can see something now.
That's it. That's
okay.
Go ahead.
All right. So I'm not going to bore you. There's a lot of stuff that Hannes has already touched on, so I'm going to try and skip over those things, and we'll start with the space frame. We've worked quite hard finishing the space frame, in a sense that we had difficulties in deciding on the antenna deployment capabilities. We couldn't get to a stage where we could actually have a complete antenna deployment system as such. We've eventually went back to basics and used the normal type unfolding capability, and then we had to look at the capabilities of having doors open up with additional solar panels, because we were really power constrained from a power point of view, and electronics wise we could compress the electronics quite a bit within the unit, even have space for a sensor board for experiments for universities, and that sort of by reducing the antenna deployment area gave us that extra space, and therefore we had to look at a solution like that. So we've done the design, it's complete, so I'll show you some of that details. You can just get the right key. Oh, it doesn't want to do this. Okay. So this is the antenna itself. It's got the tape measure antennas that unfold. And you'll see on this plate at the top, there's a hole in the middle. That's where the connections, the coaxial connections will come in from a transmitter and receiver board. And there's a little PC board that fits at the top here, which I don't show in this picture, which then it's got a little PC board section that fits underneath these tape measuring parts. And then that makes the connection from the actual coaxial cables to these, and we can even have little matching circuits in here to match the impedance quite nicely. So that's design is done. We had to make this part of the corners of the satellite, this plate here, as we couldn't make the pillars come right through, because we had to populate the boards from the top. And we had a problem where we can assemble this and make it a connectivity to the actual frame. So we made some changes. Then this whole here is what we added for the camera. We started on the camera. We've got the camera. We've mounted it. It seems to work pretty well. I'll show you some photos of that. So this is the space frame with some areas being made transparent. So there's the actual micro switch, which will fit on the bottom board. We didn't show the bottom board in this time, and there's a little pin that comes out at the bottom of this frame, which will actually be the switch that it's called the deployment switch that will switch on the satellite. So there's two functionalities that we need to enable on this. There's the remove before flight switch, and then this little switch here. So we've implemented this. And this frame base here, we've also made a cutout in it, and there's a little pin spring-loaded that will push against this micro switch. So we've got all the necessary requirements from a space flight in here. There's also additionally there's spring-loaded springs at the bottom, 2 legs of them, and the purpose of those 2 spring-loaded units at the bottom is when the satellites are mounted in the space frame, they could have 3 of these AfriCUBE satellites, and as they get pushed out with a spring from the back, they need to push away from each other to a certain extent. So there's those little springs there to push them away from the satellite next to it. So that I'll show you some details around that. So this is all the components of it. So it's quite a lot. We've got all the boards that sits here. We've got the side 4 side pillars. We've got these opening panels here with extra solar panels. There's actually solar panels between here as well, and the ones that's opening. So we can have, let me think here, it's 4 solar panels plus 4 on the doors that opens. It's 8 plus the one at the top. It's 9 solar panels that will be available, generating us power. So that gives us that benefit of having enough power to operate all the capabilities we want. This section at the top is the antenna deployment plate, and then these we've got inner spaces that just sits in between the boards when it's assembled. So that's sort of how it works. It all mount to the base plate, and it's all screwed up to the top. That's the coax. I think I've showed you that. There's the actual antenna deployment plate, which is mounted to the top plate of the actual frame, and you can now see where the mounting of the camera comes through, and where the section of the coaxial cables will come through. Here's the hex nuts that will connect the actual tape measuring parts in here. So the screws will come in here, and the hex nuts will sit in there. That's the top part of the space frame, just below the antenna deployment. You see this one. This is the representation of one of the boards inside. So at the moment we've got the SDR receiver board, we've got SDR transmitter board. In fact, we've got 2 transmitter boards. We've got a low power one that's about 220 milliwatts, and then we've got a high power version of 440 watts, which will, not watts, milliwatts, sorry. That will give us the capability, if we have enough power, we can switch on for 40 milliwatts. If we don't, we can run on 220. Onboard computer, that's already existing. We've got, I think, 1 more generation of that. We've got 1 bug on that board, and it should be complete. Magnetic stabilization board, we've done. Power supply management board, and I think Hannes alluded to that there's some bug there that we need to fix. Separation and experimental board is at the bottom. That will have the science experiments of the university on it, and then we have space for 1 more board. In fact, by changing the assembly, we actually made space for 2 additional boards. One is now for the space experiments, and then we've got the extra board, which will we're looking at maybe other options. So this is another visualization of it. It's got all the areas, 4 corners, 7 PC boards, 4 solar panels on these sections that open up. So they all open up independently from opening up from the antennas, and I'll show you the antennas will be wrapped around like this, and these boards will be closed with, and they will all be controlled by fish line assembly. So there will be a fish line covering these panels, and the fish line pulling in the actual antenna type measuring sections, and then that will be burnt off, and these panels will open and antennas will open. This is just more details on the actual sections. This is another view of it, but you can now get the view of how this is assembled. That's the side panels where the solar panels come in. There's a solar panel on each side of this center piece. So this is aluminium based, and then there's another PC board here with all the solar panels, and one on the other side. I'm not going to bore you with all the functionality. I think Hannes has covered this, so I'm going to sort of go over that. Then a satellite beacon. So we can have slow scan TV, AFSK, possibly LoRa. We're still experimenting with it. Possibly Whisper as well. and that's sort and in the camera, the slow scan TV camera capabilities. That's all sort of an experimental at the moment. We're working on the software. I think it works pretty well. Some of the tests that Hannes has got in Pretoria works pretty well, and I'm just finalizing the actual final messages of it. So this is the DSP signal processors. You probably saw this morning when I talked about AfriCUBE. This is the principle around this. It's quite straightforward, using the same MSI SDR like Hannes explained, mixes. All this is done in software and GNU radio, and then RF out, and then we mix the beacon signals that come in with the RF of the transponder, and we send it out. This is the command capability. I have just made a couple of additional changes to the command capability, where I got it to work with built-in phase lock loop, where the frequency, if the carrier of the frequency is drifting due to Doppler, it will actually pull it in and center it automatically. Therefore, our command capability should be pretty good. Even with Doppler, we don't actually have to be that accurate on the transmitting of the command signals. Even if it drifts a bit, the actual satellite will pull it in automatically. I've got a 10 kilohertz locking capability, and I can probably improve that, but I think for now that's probably good enough. So this is a remote configuration. So this is what we can configure remotely. It's quite impressive. If you think of the internal workings of the satellite, can totally be configured. We can change filters, we can change filter sizes, we can change beacon levels, transmitter levels, FM deviation. We can change almost anything you can think of a communication block. If you think of a super heterodyne receiver, if you think of what you can do in a super heterodyne receiver, you can do much more with the fact that it's all software. So this is all as parameters we can set from ground. We can set AGC levels, a minimum and maximum level, gain. The options is almost unlimited, and that makes it very, very powerful in a sense that once it's in space, you're not locked down to the preset configurations that was set at ground, because you cannot think of all extremes that the satellite could be exposed to in space. So therefore, this capability that we would have to be able to configure all this capabilities from ground is really a powerful feature. In fact, if we can, we could probably reconfigure the whole system to have a total new beacon or new modulation capabilities. That's really possible, and I think that's the probably what we're going to look at the end if we have time left. But for now, we're just trying to get the basics done and working. I'm not going to go through all the functionality. It's just the specifications, so I'm going to run through that. So this is the receiver board that Hannes showed you. So these tests were done with not this physical board yet, because we've still got the DC carriers and things in the middle, which will be offsetted with some capabilities in the newer version. We've got a 60 dB AGC capability, which is quite nice. Therefore, if somebody really overdrives the satellite, it will protect itself and it will not overdrive the outputs, which is really nice. We've got about 103 dB gain across the whole satellite, which is quite nice. We use decimation on the input of the SDR. So we take single input at 6 megahertz sampling rate, and we decimate down to 240 kilohertz. So that gives us, I think I can't remember the exact figure, but probably about 9 dB extra signal to noise capabilities, which really makes a difference to a very sensitive receiver. So here's the transmitter, which Hannes has showed. We've moved the beacon to the bottom. In fact, I've moved it a little bit further away, not to desensitize any receiver sitting and listening yet in the normal spectrum area. I got better filters working in here, so there's no intermodulation between these two, so that really works well. I've got very nice signals now working with that. Startup sequence, there's quite a complicated process that the satellite needs to take or go through steps when it gets deployed. Remember that micro switch that I was mentioning? That micro switch then starts up a sequence, and these sequences then start up the satellite, and it's only allowed to deploy antennas at a certain stage and a certain time, and so on and so on. So there's a lot of logic around that. I think that's the parts we start working on now to get all these sequences in succession, so it does start up correctly. This is just a block diagram of that description. We've got a remove before flight switch that, for instance, just before they put it in the actual space frame, they need to remove this little connector, or if they deploy it from International Space Station, they'll remove this little pin. And this is a separation switch. We will then switch on everything. There's a solar panels, onboard computer, and magnetic stabilization board. And there's electronic battery disconnect capability. This is just more logic around the remove before flight switches and so on. This is the power supply that Hannes has mentioned. This is the power supply just broken down in a block diagram, 3 volt, 5 volts, and so on, and the kill switches that's required. We have to revisit this section. We underestimated the 5 volt, the current consumption, and we've got a logic problem where that if we have power on the solar panels, the normal operation will start up and it will connect the battery and work. But we don't just want that capability. We want, if the batteries are full and we have a reset from the CPU, we want it to start up automatically with no power on the solar panels. So that logic we need to fix. It's just another view of that. Basically, this is the onboard computer. This is the space ready compute module from Raspberry Pi. We use the version 3 because of power consumption. The 4 is a bit too hungry on power. So this is the bottom board is the board we've designed, and this is the normal space ready CPU. Now this CPU we can get in different models, ones with internal flash and ones with that can only use the SD card that you can see in this diagram here. So we will probably use the one with quite a big internal SD, and then if that fail, hopefully we can make it forced to start up with the external SD, and that's some logic we can program internally with so many. If it resets within a certain time for a certain period, we can possibly get it to connect to the external SD and start up with that. So that's sort of a fallback on memory. Yeah, there's one thing that I want to, sorry, I just want to go back. There's one thing we've got onboard watchdog that which will reboot. So there's a software watchdog and there's a hardware watchdog. So if the software watchdog has failed, eventually the hardware one will reboot, and then there's a count on the hardware reboot. If that reaches a certain point, then that's when we're going to switch to the different SD cards. This is an illustration of how we're gonna, the little fish line you can see running across here. I don't know if it's clear, but there's these resistors that's gonna heat up. We might use something else than the resistor, something that we can use multiple times. But that's sort of the principle of how the doors will open and the antennas will be released. So if you use a resistor, it's normally a 0.125 9 ohm resistor, and that will reach 150 degrees Celsius, which is normally good. I think we've found some tungsten type material which we can reheat a few times. So if the deployment didn't happen, we can retry it quite a few times. And a resistor, we've only got maybe 5 or 6 times, and then it's blown. So I think the other option might be better. So I did explain earlier the little micro switch that's at the bottom when it's deployed. Here's an example of the actual remove before flight switch. And there's an example of how the little pin looks like on the space frame that will be used to switch on the satellite. This is the little spring-loaded units that we're going to have to put on 2 of the legs, so the satellite will separate from the other satellites when they get launched. So there's quite a bit of theory around this, the plunger itself, the pressure it needs to push out, and so on and so on. But these things can be purchased off the shelf, so I don't think we want to try and make one ourselves, but you can if you want to. There's an example of one that you can purchase off the shelf. It has to be 2 opposite legs that we can have it, and then we're only going to have 1 micro switch on the other leg to start the satellite. But we've noticed that some satellite manufacturers or designers has put a switch on both sides, so that if one fails, we've got a separate one. Maybe that's something we will look at, but for now we just got the 1 micro switch. This is a photograph taken of AfriCUBE sats that's been launched from the International Space Station. So these little spring-loaded legs will then separate them from each other, and they will slowly separate from each other as they get launched. So we still have to do a lot of testing, a lot of vibration tests that needs required on the space frame with fully assembled and so on. So there will be vacuum tests and all kinds of other tests involved, but we're starting to look at what we need to do to get ready for space. There's some logic of those resistors that will be connected, and now we're going to have logic to switch the antennas and switch them on and off. What's quite nice, if you look at this specifications from the satellite, this area, if you look at the 4 pillars, that's the 4 corners of the satellite here. Now you see they do allow us to use this space above the column. So if you look at that, so this area here can actually be used as well. So this is the area that we're using for the actual antennas here. Not our satellite won't look like this, but we have the four of them. So we'll use this measuring tapes to wind our antennas. We can have 2 antennas, one for 70 centimeters this way and one for 2 meters the opposite way, as you can see here. So that will be wound around this area, which can be used, so we're not limited for space, and that will work quite well for us. Here's an illustration of a 3D printed top section of the actual antenna deployment. This is the exact length as we're going to sort of mount, calculated. We haven't matched them to a matching circuit yet, but we just 3D printed the whole satellite and see if all the boards fits in and see if everything works. So I think the next step would probably be to manufacture maybe 2 units, one a flight unit and one for testing or for engineering, and take it from there. So battery power. So if you look at this, I just put this slide in here so that we can sort of look at what is our maximum power usage. So we're going to look at the 3, this level here. So we look at, 3A, 307. So desktop idle, no Wi-Fi connected. In fact, I can get it even lower than this by switching off certain functionality in the Raspberry Pi. I think I got it down. If the CPU is not used, actually I got it down, I think, to just under 200 milliamps. But if the CPU is working quite hard, this is probably the level we're looking at. So it's the 3A that we're running. Sorry, this one here. So that's sort of the level we're going to run at 225 milliamps. And then we need to add a power amp stage power that needs to be added to this. So we should be in the power budget that we want to be in. Is this 1.13. And that includes a DSP signal onboard computer and everything else except the if we run the high power 440 milliwatt, it draws quite a bit more power. So we need to start looking at launch vehicles. How are we gonna, which launch vehicles, and the specifications of the launch vehicles and the launch units is slightly different. So we need to accommodate because you cannot choose upfront sometimes with which company you're going to fly. So I think we looked at all the different specifications of the different launching companies, and we're trying to make the space frame as generic as possible so it could be used in any use with any company. So we've got all these companies for low orbiting space. That's probably the guys, and then for below 400 or 160 to 2000 and 400. This is the other companies that basically offer the capabilities. So 1U satellite, the limit is 1.33 kgs. So we really stress for weight, and we cannot use too many hardware on board. So the companies that we looked at mostly from a design point of view is these two companies, and they mostly deploy at the 400 kilometers. Ideally, we want to go a little bit higher, but we'll see what's available. This is the company SpaceX, Rocket Lab, Space BD, NanoRocks, and D-Orbit. And we'll probably start engaging with them to look for space capabilities. This is just some more details, other specs that's important, or the area that can be used. If you look at this spec that you see here, is quite different to the spec I showed you previously. So we are now limited to the worst case scenario, which is only 6.5 millimeters and not the previous spec. So we did wound the tape measures around, and we're still fine. This is the satellite control, the software that will control everything. I'm not going to bore you with all this. This is just basically commands that get sent up to space that will then configure. Remember, I mentioned all the settings that we can configure. So this is basically it. That will set the satellite in different modes, different telemetry modes, and so on and so on. And it even's got some logic around it that if the battery's levels get low, it will put itself in a very low power mode where it only have a very low level beacon and only listening for commands. So, it will protect itself and that kind of thing. So that logic is all built into it. That's the logic. I'm just explaining it in more detail. I'm not going to go through all this. This is all the modes and how we configure it. I think that's a bit boring. This is sort of the band plan. So the thinking is to have CW at the end, AFSK modes in this section, I think 10 kilohertz bandwidth, then 30 kilohertz digital, and 12. I think this can't be 30 kilohertz. I think the total is 30 kilohertz. I think there's a mistake here. No, 44.1 kilohertz is our bandwidth, so it's correct, 30 kilohertz. And the 12.5s for the two FM channels. And then the downlink is just a copy of that. And the beacon, and then sits a little bit separate from it. I think the beacon frequency I've moved a little bit, so this is not 100% accurate. This is the part that I just got working probably about 3 weeks ago, is the capability to have a carrier lock on the command, the receiving antenna. So we're also going to send this locking frequency down through APRS so that we can see that we're still coming in, and the receiver on the satellite is still listening at the center point of our command frequency. So I've got this working pretty well. I was jumping up and down when I got this working. So the phase lock loop is all done with software, and it really works well. So it will basically give us a 10 kilohertz area from this point here to this point there, where it will lock to the carrier depending on the Doppler shift a little bit up or down. So that will give us probably very good command capabilities while the transponder is running. This is doing it at the same time, so it's not that you need to switch off a transponder. All this happens all at the same time, multi-process and multi-threaded. So it's really quite an achievement. I think from my side, I'm really happy that this is working. This is just a description of how I demonstrated how the lock work. I think this one is, no, it's not a video. I thought it's a video. But basically, you see this little red carrier here in this section here. So that is the carrier I transmitted, and this is the carrier out, and the phase lock loop basically pulled it straight into the center. It doesn't matter where this red carrier would move up and down. in this frequency, and it always pull it in right in the center, which is quite nice. And it did it very quickly. It's like microseconds. So I'm really chuffed at how it worked. Direwolf, this is the AfriCUBE demodulator that we're using. I'm using a C library from Direwolf to do the AfriCUBE demodulation. So I'm piping the audio from GNU radio to Direwolf to do all the packet decoding. And then that will get stored in a text type of file format, which then another process picks up and then controls the satellite. I think this is no, this video doesn't want to play. Okay, I was hoping to show you how the actual signals look like, but that doesn't seem to work. This is just the signals again, slow scan TV, APRC, Dublin voice. So unfortunately, I can't do the videos for some reason. Ground station, I'm not going to bore you with that. I think Tom has really done a fantastic job this morning to show what he's developed, and I think that would be ideal ground station for our satellite. And then obviously using SatNox as a secondary backup for something like what Tom has done would be fantastic to monitor and control the satellite. It's just some details about SatNox and how it works. I'm not going to bore you with that stuff. Here's the camera module we're using. We've selected this camera as it's been space ready. It's been used in space before, and I'll show you some details. So we're using the same. So in theory, we should be able to have a similar type of capability. Let me see if this link works. Yeah, it's just more specifications. Okay, so yep, that's the one. This is the antenna, and this is where the camera is mounted in the actual top section here. It actually fits quite nicely, and it just misses the top board. So there's like 1 mm space between the camera and the top board, which is perfect. This is different camera modules and lenses that you can use. So we looked at the ones that flew before, and the ones that we're looking at specifically is the ones with the infrared capable or rejection of infrared, so that we do not have too much sun reflection. So the IR cut frequency, is the important part. So we selected the one with the IR cut frequency, which is quite important. This is the actual Raspberry Pi unit, and then you have this little kit with this lens on top, which runs. So depending on what quality camera you select, you can get up to 8 megapixel of sensor capabilities, and it can give you 1 megapixel basically at 30 frames, which is video as well. Not that we're probably going to do video. I doubt that because of the bandwidth of our beacon. If on the AfriCUBE, where we have wide bandwidth on the 10 gig transponder, there I think we can probably send video down, real-time video, which shouldn't be a problem. But in AfriCUBE, definitely not. We don't have the bandwidth.
Anton, we've got 2 minutes left.
Okay, I think I'm basically done. That's just where it's been used before. That was their photos, pretty good. That's just how we did the test. This is a test unit that's going to fly in Bakar. CubeSat test requirements and questions.
Okay, Anton, thank you very much. As always, interesting presentation.